Hello, this is Bob McFetrich with Beckwith Electric. I'd like to thank you for downloading our training session on the M-6200A regulator control. And this session is for the basic settings. Now, this session will be using version 020601 of our TapTalk 6200 software, and also version 010500 on the firmware within the 6200A itself. You can download the latest version of TapTalk on our website if you go to www.beckwithelectric.com, and then you can go to Customer Support Download Center. So the 6200A is the most recent in a series of controls that Beckwith Electric has developed for single-phase regulators, as seen here. Now, our 2001 platform was developed for both transformer LTC controls and single-phase regulator controls, and it was also used with the GE regulators as a GE 2011. But the latest for single-phase regulator controls only is the M-6200A. So it differs from the 2001 platform in that it is not to be used for LTC control, as it does not have any capabilities for paralleling of transformers. So it is less expensive, has similar functionality to the new 2001D, but is made specifically for single-phase regulators, and does not use the adapter panel concept of the C, but instead has a adapter kit concept that is handled in a different session of this presentation. So we will be talking about the initial offerings or the basic functionality and configuration of the 6200A in this session. And we will be assuming that you are cabling to the front port of the USB with your TapTalk, or you are doing a file new offline. So we will be going through each of the basic settings, showing you on the TapTalk where those settings are, what the parameters for the settings are. And if you want to follow along, you can have a unit powered up, and if you are cabled into the USB and connected, you can follow along. If you do not have a unit, you can download the TapTalk software off the website, and if you just do a file new, then it'll allow you to look at all the configuration screens we're going to see without requiring a control to be present. So we're going to talk about the basic settings, and those are the traditional settings that were typically the only settings found in the old electromechanical regulator and LTC controls. So real quickly, a basic understanding of why we need a regulator or an LTC. But first, the settings we're going to be covering will be band center, bandwidth, time delay, and outputs. So these are the only settings you need to get a regulator or LTC control to start to regulate around the proper voltages. But first, let's go back and look at the basics. The reason we need an LTC or a regulator is because we know the voltage across our distribution system is going to fluctuate, and it's going to fluctuate due to fluctuations in load. As the load changes, current going through the impedance of the cable and the distribution transformers will cause a voltage drop, and therefore the more load going through that impedance, the bigger the voltage drop, and the bigger the voltage drop, the more we have to regulate the voltage. So ANSI standards dictate that in the US nominal voltage is 120 volts, and we need to be plus to minus 5%, which means we need to try to keep the voltage between 114 and 126 across the entire distribution circuit. So we know that voltage will vary due to load. We know that that variance has to be regulated in some manner so that we can keep the customers between 114 and 126. And the way the regulators or LTCs do it is they are tapped transformers that have multiple windings, and typically with each winding we can vary the voltage a certain percentage. So all single phase regulators and the majority of LTCs will have 33 taps, 16 raise, 16 lower, and a neutral. At the neutral position, the voltage coming in is the same as the voltage going out. The incoming voltage is typically referred to as the source side voltage, and the outgoing would be referred to as the load side voltage. So, if we do the math and we have 16 taps on either side and we can regulate plus to minus 10%, we will see that what that equates to is 3/4 of a volt secondary per tap. So, with each tap, I can either raise the voltage on the load side 3/4 of a volt secondary, or I can lower it 3/4 of a volt secondary. And at the neutral position, the voltages will be the same. So the goal of the regulator or the LTC is to keep the voltage within a preset boundary. Now, with that in mind, we're going to look at our tap talk, and we're going to open it up, and we've done a file new in this case. I'm not online. You can see down here I'm in file mode. If I were online, it would say connected in either level 1 or level 2. But I'm in file mode here. I've created a new file. I have not saved it yet, so it does not have a name. And we're going to start by doing a file setup tap changer type. And when we do that, this screen should appear. And in this screen, we can come down under regulator vendor, and we can select the regulator vendor we're going to be attaching this control to. So we have a Siemens, a Howard, a GE, or we have 3 different types of Coopers: a spring-driven, a direct-driven, and a quick-drive. Now, once we select which of the regulator manufacturers we want, then the following screen should come up. And it's going to pre-populate certain settings down below off of that. So in older versions of firmware, we had to set each of these settings uniquely, and we had to know how to set them for each of the manufacturers. But in the new version of TapTalk and firmware, we now can just simply select the regulator manufacturer, and then the software will pre-populate it, and it'll show you what it's selected for each of those parameters. And if you want to, you can still overwrite any of those parameters, but this is what's selected. Notice also that above that we have to check which type of regulator, whether it's a type A or a type B. Now we're going to cover what the differences between an A and a B are in a future session, but you can look at the nameplate of the regulator and you'll see either the words type A or type B, or in the case of Siemens, sometimes you'll see either standard or straight or inverted. A standard or straight is equivalent to a type A, and an inverted is equivalent to a type B. So in this first screen, we can select the type of regulator and the manufacturer of the regulator, and we have automatically pre-populated certain settings that we're going to discuss later on. Now, the first unique setting we have to put in then for our system is what the voltage we desire to have on our system. So in this case, if I desire the voltage to be 120, we're telling the regulator control that we want to keep the voltage somewhere around 120. And the amount or the area that we're going to consider good around that center point is referred to as the band width. So the band center is the center point of that allowable voltage range. The band width is actually cut in half, half applied above and half applied below, and together we then have our operating band. So as long as the voltage is in this area, we are considered in band. So if the voltage is below the upper band and above the lower, we are in band. So the band center of 120 sets the center point. The bandwidth of 2 gets divided in half. Half of that bandwidth gets applied, in this case 1 volt, to generate the upper band of 121. The other half, again 1 volt, will be subtracted from the center to set the lower band of 119. And as long as our voltage is between 119 and 121, we are considered in band, and the regulator or LTC control will not attempt to tap. If we exceed the upper band, we are out of band on the high side, and we will call to lower the voltage. Likewise, if we were out of band on the low side, we would be calling for a raise to try to raise the voltage to get it back in. And remember, we're expecting 3/4 of a volt per tap. So, with the band center, we are setting the center point of the acceptable voltage. And in the software, we would go to do File, Setup, and we would select Set Points. And when we do that, this screen should come up. And right here, we have the band center value. And with all of our settings, if you notice beside the setting, it'll show you the legal range. In this case, 100.0 to 135.0. And the scale, in this case, volts. So because I have a decimal point in one position to the right, that is the resolution. So I could enter in 115.7 and that would be valid, but 115.75 would not. So beside each setting, we are showing you the legal boundaries of that setting and the resolution provided by the setting and the scale of the setting. So in this case, the band center, the default value, and when you do a file new, every value that's populated is the factory default value. So in this case, we can see the factory default value for the band center was 120.0, and the legal range for this setting is between 100 and 135, and this setting is in volts. And we have a 0.1 volt increment resolution. The bandwidth is right below it, and in this case, legal bandwidths are from 1 to 10, and the default is 2. Now, to change the value in TapTalk, I can do it multiple ways. One is I can just put my cursor over this position and type in the new value, say 3 volts, or I can click on the sliding bars and it'll increment it in 0.1 volt increments until I get to the right value. So I can either use the slide bars or I can manually enter in a value. So now we have set our band center and our bandwidth. We now have the allowable range of voltage that we're going to operate in without taking an operation in either direction. And notice, by the way, that these are forward power settings. We have similar settings in reverse power, and those will be discussed in the session specifically on reverse power. So for now, we are concerned with the forward power settings only. Now, once we exceed a band, in this case, we've exceeded the upper band, so we are going to want to lower the voltage. But we do not immediately lower the voltage. We will wait a finite amount of time, referred to as the time delay, before we take action. And there are two purposes for the time delay. Number one is load will fluctuate. For instance, when an air conditioning unit starts up, the motor will draw more current until it gets up to rated speed, and while it's drawing more current, it'll cause a voltage drop. But once the air conditioner gets up to rated speed, the voltage will come back up as the current goes down. So if we were to have many air conditioners coming on at the same time, we would see a temporary voltage drop, which may cause us to want to lower the voltage. But if we did that, we would just have to raise it again once they all got up to speed and they started drawing less current. So the nature of motor load is such that as it starts up, it requires more torque, therefore more current, which can create a voltage drop. And we want to try to ride through that voltage drop before we attempt to correct it. and that will save us operations on the regulator or the LTC. The other reason to have a time delay is to coordinate. So there are many devices out on our distribution system that can change the voltage. We can have either LTCs or bus regulators or feeder regulators inside the substation fence. We can also have downline regulators, and we can have switch capacitor banks either inside or outside the fence. So we need a way of coordinating all these devices so that we can determine our strategy when a voltage needs to be changed, which device we want to try to use to correct it first. And so that would be the second point of the time delay. So the time delay is in seconds. And as you can see, the time delay in this case, we've just made a new change to the software. It used to be the maximum time delay was 120 seconds. We have now increased it to 360 seconds. So we have a time delay. You can see that the legal values in this case are from 1 to 360. There is no decimal point. That means the resolution is in 1 second increments. Now, notice that it says definite time delay here, and we have another setting over here called time delay selection, and our two choices are definite and inverse. Definite time delay is the historical approach to the time delay, and what that basically says is if I select 30 seconds, I have to be out of band for 30 continuous seconds before I start trying to correct the voltage. With the inverse time delay, it acts a little differently. So let's look first at the definite time. So the definite time, in this case, if the voltage is up, it goes back into band prior to the 30 seconds, we're not going to take the tap. Now, after a while, it goes out of band again, and in this case, if we stay out of band for greater than 30 seconds, we will take the tap and we will start to lower the voltage. So with definite time delay, the way this is going to work is we need to be out of band for more than the time set before we attempt our first operation. Our other selection would be inverse time. And with the inverse time delay, we would select the inverse here, and then notice the text here would automatically change from definite to inverse. With the inverse time, it works on the same principle as an overcurrent relay. With an overcurrent relay, the more fault current you have, the faster the relay is going to operate to try to isolate and remove that fault current. In the case of the inverse time with a regulator or LTC control, the further the voltage is outside of band, the faster it's going to time. And that time is a fixed curve inside the control. So this is the curve, and you can notice that the bandwidth, half of the bandwidth, will cut the time delay in half for every half it's out. So basically what this says is, if the voltage is not that far out at all, we're going to do the full time delay. But as the voltage gets further and further out of band, we're going to keep reducing the time delay to a minimum of 10% of the setting. So in the case here, if we start with an inverse time delay of 120 seconds, we know that if we're within one tap of band, we're going to wait the full 120 seconds. But as we get further out, we're going to keep cutting the time delay down, and we will tap as fast as 12 seconds, which would be 10%. So we take the sense voltage, we subtract that from the band center, so the amount we're out of band, divide that by the bandwidth divided by 2, and that'll give us our time. So in this case, for instance, if we were at 123 volts measured, and our bandwidth was 3, and we were going inverse time delay of 120, we would take our measured voltage, minus from that the band center, and then divide that by the bandwidth of 3 divided in half. From that, we could see that we would get a value of 2, which basically means if we go to 2 here, we have cut our time delay in half. So, what are the advantages, or when would we use the inverse time versus the definite time? If we have regulators inside the fence, whether it's regulators, LTCs, we can double our definite time delay, go inverse, and in theory we will reduce operations. Because what's going to happen is if we take our normal time delay, say 30 seconds, and double it to 60, if we're just a little bit out of band to where the customers are not being negatively impacted, we're going to wait twice as long before we tap. That gives the system more time to settle in or for other downline devices to correct the voltage, therefore reducing the number of operations on our regulators or our LTCs. So inside the fence, where your regulators or LTCs are going to be more expensive than downline regulating devices, we'd like to reduce the operations if possible, and one way of doing that is to go from a definite time to an inverse and just double whatever your definite time is, make it twice as large for the inverse. The other benefit is if we get several taps out of band, let's say that we've just lost a lot of load. Maybe we've got an LTC with 3 feeders and we've had 1 or 2 of the feeders trip out. The remaining feeder is now going to see high voltage because we've lost a lot of load. And if we were to go definite time, regardless of how far out to band it is, we're still going to have to wait the original 30 seconds. But with the inverse time, even at 60, if we're 1 tap out of band, we're cutting it 2 taps out, we're cutting it in half. And if we're more than 2 out, we keep cutting it in half. So if we're 2 taps out, we're going to go from 60 to 30, right back to where we were. If we're 3 taps out, we're actually going to go down to 15, which is going to be much quicker. And the minimum we'll wait is 6 seconds. So we can be tapping as quickly as 6 seconds as opposed to 30 seconds. So when we have a large discrepancy of voltage where the customer is experiencing problems, we can be much faster to react. Now for line regulators, we would typically recommend going with a definite time, except for 2 conditions. One where the regulator is close to or just downstream from a recloser, and the other is if we have a regulator that is feeding an industrial facility where their load varies greatly multiple times a day. For instance, with a stone crusher or a car crusher or a sawmill, when they're in operation, you can see large voltage swings. And if we were to set it to inverse instead of definite, we would give them a much flatter voltage profile, but in that case, it would be at a cost of additional operations. The other possible one would be for regulators coordinating with upstream reclosers. So let's take a look at that. In this case, we have a feeder breaker, we have a set of midline regulators, and then we have some 3-phase reclosers just downstream. Now, if we only have a few customers located on this section between the regulator load side and the 3-phase recloser, what's going to happen is when we have a fault down here and the recloser goes to lockout, we're going to lose all this load, which is going to drive this voltage high, and these customers will experience high voltages. Likewise, when we pick the load back up, when we close in and we pick up all this load, these customers in between can experience a low voltage. So in this case, we know that we can have the possibility for voltage swings due to the operation of the recloser downstream, and we would therefore want to possibly look at an inverse time versus a definite time. Now, the other part of time delay is in coordination. And we talked about this earlier, but we could have a LTC or bus regulators or feeder regulators inside the fence, and then we can have downstream line regulators. And when we do that, we need to coordinate them. And the reason we need to coordinate them is because regulators are what's referred to as unidirectional. What that means is when they operate, they affect the voltage only on the load side of the regulator, not the source side. So because of this, we need to do our coordination. And let's look at the next slides to get a better reason why. So here we have zoned our regulation. So again, the regulator can only affect the load side of the regulator, which would be this side. So for regulator 2, the zone of voltage it can impact would be this portion of the circuit right here. Anything upstream of that, it cannot change because that would be on its source side. It can only affect the voltage on the load side. So the zone of operation of regulator 2 is in the smaller box. Regulator 1 cannot affect this voltage here, but it will impact everything down below it because that is all on its load side. So now we have a bigger box for zone 1, or the regulating zone of regulator 1. So if we were to assume that the voltage was low across the entire circuit, and we were to allow regulator 2 to raise the voltage first, when it raises the voltage, it can only impact this portion of the circuit. So it has brought this portion of the circuit back into band, but this portion of the circuit still has low voltage because this regulator cannot adjust that voltage. Therefore, this regulator will have to raise the voltage to get this section of the circuit up. But in doing so, it also raises the voltage to the second part because, again, the second part is on its load side. So now this voltage has gone too high, and now the regulator 2 is going to have to step it back down. So you can see that if we do not properly coordinate our regulators, we can increase the number of operations. So if we would allow regulator 1 to operate first, in this example, if the whole circuit was low, we would have only had 1 tap as opposed to 3 taps. So, the general rule for coordinating regulators is the regulating device closest to the source will have the shortest time delay, and the time delay will be increased with each set of downline regulators. And a typical rule of thumb is between 10 to 15 seconds of time delay increase. So if I were running, say, 45 seconds on my LTC, and I had a set of downline regulators, I would add 15 seconds and I would set their time delay to 60 seconds. So in this example, if we set this to 45 and this to 60, if this portion of the circuit was the only thing out of band, it would tap and be corrected in 45 seconds. If the entire circuit was out of band, because this portion is still out, we would again tap in 45 seconds. But if the only portion of the circuit out of band was down at the end, then this one would be in band and would not tap. This one would be out of band and it would time to 60 seconds and then take its tap. So the disadvantage in coordination is that you are having to slow down the operation of your downline regulators to give the upstream regulators time to operate if needed. That's another reason in the previous example that we may want to use inverse time, because that line regulator may have a time delay of 75 or 90 seconds. So when that recloser operates, we could be waiting, if we're going definite time, upwards of 90 seconds before we start correcting the voltage. Where if we were to go inverse time, it would be corrected much quicker. Now, the next setting we need to talk about with timing is in our reset. So the time delay reset occurs when you start the time, but before you finish or expire, you come back into band. So in this case, for instance, if we're out of band for 3 seconds and then we come back into band, what do we do with the time delay? If we set it to instantaneous, whenever you come back into band, you reset the time delay back to 0 and it has to start counting over. So for instance, let's say we really had a 30-second time delay and we were out for 28 seconds and then we went back down. When we come back up again at this point, we have to start back at 0 and we need to stay above for 30 seconds before we tap. With the integrating, it actually counts backwards. So for the same example, we're out for 28 seconds. Now if we come back down for 2, we're at 27:26. So now when we exceed, we only have to go 4 additional seconds to get to 30 and take a tap, because we're starting at 26. So the general rule of thumb is integrating time delay will increase the number of operations slightly but give you a flatter profile on your voltage, where instantaneous will decrease the numbers of operations, but if you're on the hairy edge, it will not always bring it back into band to give you a flatter profile. And here would be the settings for integrating versus instantaneous. So we would select integrating if we wanted a flatter voltage profile, knowing it may add operations to the regulator or LTC. And we would select instantaneous if we wanted to have fewer operations on the LTC or regulator. We're to the final part of this session, and that is we have exceeded band, and we've exceeded band for longer than the time delay. At this point, it is time for the regulator to take action, and the control needs to send either a raise or a lower command. To do that, its physical output will be interfaced to the motor in some form or manner to the regulator or LTC, whether it's spring charged, whether it's direct driven on the motor. We need to get an output to drive the mechanism of the regulator or LTC to take a physical tap. Now, there are different ways we can do an output. The first way, which was traditionally done with single phase regulators, is what's called a sequential or continuous mode. In this example, we have exceeded the band at this point. We have gone through our time delay at this point, and now we are going to get a physical output to lower the voltage. So the time delay is what triggers the output to get up. Crossing the band for more than the time delay energizes the output. What turns the output off, though, is the voltage actually coming back into band. So whether we need to take 1 tap, 3 taps, 8 taps, the output will be sealed up and continuously driving the motor and causing taps until the voltage comes back in the band, and at that point the output will be turned off. The advantage of a continuous mode is it's the quickest way to get back into band if you're multiple taps out of band. The disadvantage can be that you can have a phenomenon called run-through or drive-through. And that typically occurs when you have a very tight band. So this say I only have a 2-volt bandwidth, like in this example. I only have 2 volts from going from the upper band to coming out the lower band. And it takes a while for a regulator control to measure the voltage, determine if it's out of band, get up the physical output, drive the regulator. It also takes a little bit of time in reverse to measure the new voltage after a tap, verify whether it's in band or not, and then make the determination as to whether to keep the output up or not. Now, traditionally, regulators and LTCs have taken anywhere from 1.5 seconds to 6, 7, even 8 to 10 seconds for them to mechanically, physically operate 1 tap. So there was no issue in the regulator control taking a little bit of time to verify the voltages and determine whether to take the output off or not. But we have regulator manufacturers now, such as the Cooper Quick Drive, where they can tap in 1/4 of a second. So in 4 seconds, it can take, or in 1 second, it can take 4 taps. Well, 4 taps at a 3/4 of a volt per tap is enough to drive through band. So what can happen is, I am lowering, and by the time I determine that I've gone low enough in band, I've taken another couple additional taps, and now I may be too low and have to come back up. So with that in mind, we would not select a continuous, and that would be for a Cooper Quick Drive, for instance. So if we select continuous, we know that the output will be turned off by coming back into band. And that would be selected off of the configuration screen. So notice on each of these windows, if the blow up window, this text right here refers to the menu off of the main. So if I were to go to select, I would have a topic configuration. If I clicked on that, it would bring up this submenu. And in this case, we are looking at continuous setting. A second method would be non-sequential. What that says is we need to take a tap, and whether we're back in band or not, as soon as that tap is completed, we will not take another tap until the time delay expires again. So for instance, if I had a 30-second time delay and I were 3 taps out of band, I would take the first tap after 30 seconds, and then I would turn the output off, and then if I were still out of band, I would time again for additional 30 seconds, and then again an additional 30 seconds. So obviously the advantage of this method is that we do not have to worry about running through band. The disadvantage is it can be a very long time if we're many taps off before we get back into band. So this method is typically not preferred. But we still need to solve the problem of running through band on the fast operating regulators. And to do that, we have a third mode, which is going to be back to our sequential, but we're going to add a secondary timer called the InterTap time. And the way this is going to work is we're going to have 2 time delays. One time delay that gets applied when you're in band and you're going out of band, and that would be your normal time delay. But after the first tap, if we are not back in band yet, we will use the secondary InterTap delay before we take the next tap. So as an example, if we were to set the InterTap delay to say 2 seconds, we would be waiting 30 seconds to do the first tap. Once completed, we would drop out our output, look at the voltage. If it was determined to still be out of band, we would wait 2 seconds and then take another tap. And if out of band still, wait another 2 seconds before taking a tap. Once we come back into band, then the next time we exceed band, we go back to our 30-second time delay again. So the advantage here is we're waiting just long enough that we don't have to worry about a quick regulator driving through band, but we're not waiting too long such that if we were 7 or 8 taps off, it would be a long period of time before we could bring it back into band. Right here. And again, you can see that that setting is in seconds, 0 to 60. So, the other type of output besides continuous would be pulsed. And with a pulse output, it says keep the output up and turn it off after one of 2 conditions is met. Either we have taken 1 tap or we have exceeded the time. So in this case, we're going to have a setting called that pulse out with time. In this case, the default is 1.5 seconds. So what this is saying is, once I get up a raise or a lower output, keep it energized for 1.5 seconds, and then turn it back off. Or if I see the operation counter increment before the 1.5 seconds is done, turn it off because we're only going to take one tap. So it does use the operation counter to determine whether to turn it off sooner. But if the operation counter is not working or not available, it will automatically turn the output off after the time has expired. When would we use this type of functionality? Well, one case is with GE regulators. As we said earlier, if we use continuous mode, once the voltage comes back into band, we automatically turn the output off. So in this case, our voltage is just a little bit outside of the band. And with the GE regulators, they use the same PT to drive the motor as to sense the voltage. And the spring that we're charging requires a lot of torque. So what can happen is when you turn the output on, the voltage can drop up to 3/4 of a volt on the secondary while it's charging that spring. So in this case, if my voltage is, say, 3/10 of a volt above the upper band, I time out, and as soon as I turn on the output to lower the voltage, and we start charging that spring, it actually causes the sense voltage to collapse back into band. Seeing the voltage back into band causes the control to turn the output off before it taps. And once we turn the output off and we're no longer charging the spring, the voltage comes right back to where it was and we're outside of band again. And we can get into a continuous loop until either the voltage continues to creep up enough that even with the output on we're still above band, or it comes back on its own. So if we were to use the pulse instead, the pulse says when I take this tap, wait for either the op counter or the time period to expire, regardless of whether the voltage comes back into band or not. So in the case of a GE regulator, this say it takes 6 seconds to tap. I would set the pulse time to 9 seconds. We want to set it longer than it takes for one tap because as a regulator ages, it can slow down. But we do not want it longer than 2 taps because if the operation counter were not to be present or were to fail, then the timer is going to stay up for the full amount and you can have it being driven multiple taps instead of one tap. So the rule of thumb is if we're going to use a pulsed output, we want to place the regulator in manual. We want to time the amount of time it physically takes to do a tap. We want to multiply that time by approximately 1.5 to 1.75, and then that's the setting we're going to put in. And in that case, that would correct this problem with the GE regulators. So we currently recommend going with a pulse setting for everything, but we definitely recommend going with a pulsed output setting for the GE regulators. Finally, if we are using continuous mode, we still need to look at setting this pulse output with time if we're going to be communicating via SCADA, because SCADA will use that same time. So for instance, if we have a regulator that takes 4 seconds to tap, when we send a DNP command to raise or lower, the control is going to keep its output up physically for either that duration of time or the operation counter input, whichever comes first. So if we set this delay too short, for instance in this case 1 second, SCADA would never be able to remotely raise or lower the regulator if it takes 4 seconds to operate. We would need to change this time to at least 4 and preferably more like 6 seconds. So the pulse width setting must be done if you're going to do remote raises and lowers via DNP. So this session went a little longer than I had hoped, but I hope you got some valuable information, and we'll tune in to other sessions upcoming on the 6200A. At Beckwith Electric, as always, we thank you for your time and being a valued customer, and we hope you have a blessed afternoon. Thank you.